Hello, thanks for listening in. It's great to have you with us. The vacuum gauge is defined by the covariant vacuum gauge condition. Any set of potentials which satisfies this first order differential equation may be referred to as vacuum gauge potentials. The most important set of vacuum gauge potentials for the classical electron are the light-like retarded null potentials, where R nu is the vector from the retarded position of the charge to the present time field point. We note here that the radial nature of the vacuum gauge potentials are indicative of their ability to describe the physics of a single charged particle. An interesting interpretation of the vacuum gauge condition is the following. In the rest frame, suppose we assign a complex exponential to the light-like vacuum gauge potentials. Vector and scalar potentials may then be interpreted as traveling spherical waves. Now let's calculate the electric and magnetic fields from these potentials. We see that the magnetic field is still zero, but the Coulomb field has inherited the same oscillating character as the potentials. It's important to say a few more words about the oscillating Coulomb field. Certainly, the idea of the Coulomb field having properties of a traveling wave are completely unintuitive, but the field in the red box, along with the potentials from which it derives, still satisfies the vacuum gauge condition. Moreover, this Coulomb field can be shown to satisfy all four Maxwell's equations in any frame of reference, but of course with a slightly different definition of the source for current density. But even with the oscillating character of the field, we still believe that it will exert a traditional Coulomb force on other particles. In other words, the Coulomb field of an electron exerts a force on another charge completely independent of its property as a radiating spherical wave. Still in the rest frame, now let's write a bilinear combination of scalar and vector potentials in a way that produces a time-averaged 1 over r squared energy flux field proportional to the electric field vector. Once again, we assume that the electron still exerts a Coulomb force, but now we've included the properties of energy and momentum flux. To make this a covariant theory, we can easily build a rest frame momentum flux tensor by writing out this antisymmetric matrix here. A Lorentz transformation will then produce the velocity field strength tensor multiplied by a fundamental charge density. This implies, of course, that the magnetic fields of the particle also carry momentum, which circle around the particle at light speed. Let's continue in the rest frame and evaluate our propagating vacuum gauge potentials at the classical radius of the electron. At this radius, the vector potential multiplied by a factor of c can be interpreted as a radial electric vacuum current passing through the radius in all directions. Inertial vacuum power can then be determined by a traditional formula from electromagnetism. We note here that the vacuum gauge electron becomes a fundamental radiating antenna, having a radiation resistance given by this formula. Now suppose we view the electron in a frame where it moves with some arbitrary velocity. We can move the charge and other constants around inside the vacuum gauge potentials to produce a set of radiating spherical pressure and velocity waves. These formulas indicate radiation in the form of longitudinal oscillations of the vacuum, but we can combine them as before to reproduce invariant vacuum power. Let's calculate the numerical value of inertial vacuum power. This is a huge number comparable to the power output of the Grand Coulee Dam. We admit here that this value is disturbing, and we really don't know how it should be interpreted. However, we do know that our theory will produce a universe loaded with vacuum energy. Unfortunately, assumptions of the equivalence of mass and energy will likely reproduce a vacuum catastrophe, but this time from a classical perspective. To avoid the catastrophe, you could just assume the energy has no mass equivalent. Thanks again for listening in. We hope you've enjoyed this short video and have a great day.